Video 7 of the Master Course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is minimal coupling, the non-relativistic case. In this book, as in most of the research applications, we will employ a semi-classical approach for the description of the interaction between electromagnetic fields or nuclear electromagnetic moments and molecules. This implies that the electrons are treated by quantum mechanics, of course, but the fields or the nuclear magnetic moments and the fields coming from these nuclear magnetic moments are treated classically. They are treated by classical electromagnetism. The fields or nuclear moments, they are not part of the system, which is treated quantum mechanically. So they are merely considered to be perturbations which do not respond to the presence of the molecules themselves. So it's, in a way, a one-way communication. The fields will enter the molecular Hamiltonian in terms of external potentials, similar to the Coulomb potential due to the charges of the nuclei. In the following, we will now derive the operators which are going to enter the Hamiltonian for the motion of a single electron in the presence of external fields. The generalization to the case of many electrons, however, is simple. However, before we look at the case of an electron in the presence of electromagnetic fields, let's just recall how one, in a way, can derive the Schrödinger equation. I mean, it's not really an exact derivation, but at least can motivate for the Schrödinger equation. And one does it by starting from the classical Hamiltonian H of a system. The Hamiltonian H of a system is in general a function of the position of the coordinates of the particles involved in the system and the canonical or generalized or conjugate momentum of the particles. And in the case of a single field-free particle, the Hamiltonian is very simple. It is just the canonical momentum squared divided by 2 times the mass of the particle. So that's the classical Hamiltonian function. Now, one can get to the Schrödinger equation by replacing those functions here, the Hamiltonian and the canonical momentum vector, by operators using the general substitution rules that the canonical momentum vector is substituted by the operator for the canonical momentum vector, and which is minus I, the imaginary I, meaning the square root of -1, times h bar times the gradient operator, meaning which is a vector operator, and the components are the first derivatives of the coordinates of the particle with respect to x, y, and z. So this is the canonical momentum operator, and the Hamiltonian becomes then the Hamiltonian operator, and that is again I times h bar times the partial derivative with respect to time. And if one now lets both sides of this classical equation for the classical Hamiltonian function act on a wave function, then we actually arrived at the time-dependent Schrödinger equation, because on the left side we have now h, the h operator, which is IH times the IH bar times the partial derivative with respect to time, acting on our wave function, which of course depends on the position of our particle and time. And on the right-hand side, we have the canonical momentum operator squared divided by 2 times the mass of the particle, acting on, again, the wave function of the particle. And if you remember that we wanted to look at a field-free particle, just a particle in vacuum, where the particle only has kinetic energy, there's no potential energy, then this, you can see this is exactly the time-dependent Schrödinger equation. This means that when we have found the classical expression for the Hamiltonian, then we can use the substitution rules in order to get to a time-dependent Schrödinger equation. So the task to do now is to find the classical Hamiltonian for a charged particle like an electron in the presence of electromagnetic fields. So the question is, how is this classical Hamiltonian normally?
Substitution rules. This is the canonical momentum. So it's a canonical momentum which we replace by minus IH bar times the gradient operator.
Derived. Well, that is normally done from another function, which is called the classical Lagrangian. In that context, maybe it's the time to mention that there are actually three formulations of classical mechanics. There's, of course, Newton's formulation in terms of Newton's laws. But there are two other formulations which contain the same physics, but mathematically they are different, expressed in a different way. And one is a formulation which involves this Lagrange formulation, and the third one is this Hamilton formulation of classical mechanics. Now, the classical Lagrangian L is a function of the position of a particle, the velocity of the particle, and time. And more precisely, it is expression for the kinetic energy of the particle, expressed in position and velocity vector, minus what is called a generalized potential. So it's the kinetic energy minus this generalized potential. And that generalized potential has to be defined for whatever system one has. And there's the condition that the generalized potential has to have a form such that when one inserts this Lagrangian in the so-called Euler-Lagrange equations, one gets back to Newton's second law. So if you have a system, you have to choose U, the generalized potential, in such a way that on inserting the Lagrangian here in this Euler-Lagrange equation, these Euler-Lagrange equations essentially become Newton's second law. And in this way, you can sort of be sure that the generalized potential which you chose fulfills Newton's law. Now, these Euler-Lagrange equations here, they are sort of a replacement or the equivalent to Newton's second law in this Lagrangian formulation of classical mechanics. And let's look at that. So you have two terms in there. You have A here, you have the partial derivatives of the Lagrangian with respect to the position of a particle. And that basically means that here that could be x, y, and z, which means that you actually have three Euler-Lagrange equations here, because you have one with the x coordinates here and there, one with the y coordinates, and one with the z coordinates. And then you here have the partial derivative of the Lagrange with respect to the corresponding component of the velocity vector, and later on you have to take the total derivative with respect to time. Now, if we work with Cartesian coordinates, then of course you have three equations. But the advantage of this Euler-Lagrange equation is that you can also use generalized coordinates, which you actually can't do. And the Euler-Lagrange equations don't change the form. They always have this form, but then you just have, instead of x, y, z here for alpha, you would have whatever generalized coordinate you have, which is not the same for Newton's second law. In this form, Newton's second law only is valid for Cartesian coordinates. Now, how does Newton's second law looks like?
In the Euler-Lagrange equations, which implies that you have to take all these derivatives of the Lagrange with respect to the components of the position vector and derivatives of the Lagrange with respect to components of the velocity, and then afterwards the time derivative. So if you all do that, then you actually will arrive at Newton's second law. Transition rules.
For our case, for the case where we have an electron where the charge is minus e, the elementary charge, moving in electromagnetic fields. Then in that case, of course, the force from which we have in Newton's second law is the Lorentz force, which we derived earlier, where we have the the gradient of the electrostatic potential minus the time derivative of the vector potential plus the velocity of our particle and the cross product with the curl of our vector potential. That times the charge of the particle is the force. And then on the right-hand side, we always have the mass times the time derivative of the velocity, meaning the acceleration. So we have to guess now a generalized potential, which inserted in the Euler-Lagrange equations gives us these Newton's second law's equation back. And of course, here we also have three equations because the velocity vector, of course, has three components, x, y, and z. Now the guess for the generalized potential looks like this. It's minus the charge here, it's minus the elementary charge, so it's the charge times the scalar potential plus the elementary charge of the electron times the scalar product of the velocity and the vector potential. By the way, the reason why this potential is called generalized potential is because it does not only depend on the position and on time, but it also depends on the velocity of the electrons. Now, if we insert this generalized potential now in the Lagrangian, remember the Lagrangian was the kinetic energy minus this generalized potential. And the kinetic energy of an electron, of course, is just the mass of the electron times the velocity squared divided by 2. And then minus the generalized potential gives us this expression.
In the exercises, you will show then that when you insert this Lagrangian in this form, where the force F is given here by the Lorentz force. So this is our Lagrangian, the correct Lagrangian for the motion of an electron in the presence of electromagnetic fields represented by the scalar potential here and the vector potential. How do we get now the classical Hamilton here in function? Well, the classical Hamilton function can be obtained from the Lagrangian by this equation here. And please note that the Hamilton function is a function of the position vector and the canonical momentum of our particle and time, whereas Lagrangian was a function of the position vector of our particle and the velocity of the particle and time. This kind of equation here, where you change from one type of variables to another type of variables, the independent variables, is called a Lagrange transformation. And I'm quite sure that in your thermodynamics course, you have seen a similar transformation, because the relation between the Gibbs free energy and enthalpy is precisely the same kind of Lagrange transformation, because you can, for example, write the enthalpy as being a function of pressure and entropy, whereas the Gibbs free energy is a function of temperature and pressure. And this is sort of the well-known relation between enthalpy and Gibbs free energy. And the relations between the enthalpy and the internal energy of a system actually is another example of these Lagrange transforms. So basically what you do is you change which variables the quantity depends on. And our Hamiltonian depends on, the classical Hamilton function depends on the position vector and the canonical momentum. Now you might ask yourself, why do we have these two alternative formulations of classical mechanics, the one with the Euler-Lagrange equations and now this one with the Hamilton function, if they are essentially the same theory as Newton's formulation? Well, you can see I write here the Lagrange generalization and Hamilton's formulation are more elegant. They're often more computational easy to use. And why is that? Well, the point is, what I already mentioned before, the Newton's second law only is valid in this form if you're working in Cartesian coordinates. And Cartesian coordinates are not always the most easy system of coordinates to use. For example, you remember for the hydrogen atom, solving the hydrogen atom in Cartesian coordinates, you couldn't do that. You changed to spherical polar coordinates. But you can't sort of write Newton's law up in the same way in spherical polar coordinates. Whereas the Euler-Lagrange equations, they always have the same form. So whatever kind of coordinates you use there, the Euler-Lagrange equations are what is called form invariant. They don't change the form under a change of coordinates. And in particular, you can also use them. For example, if you imagine that you are considering the motion of a particle in a ring, sort of in a two-dimensional plane, in a circle, in a two-dimensional plane, where in Cartesian coordinates you would have to use, and if the radius is constant, so a circle with a constant radius, in Cartesian coordinates you would have to use two coordinates, x and y, whereas if you change to spherical coordinates, you actually only have an angle, you only have one coordinate. And so you could write up the Euler-Lagrange equation just for this single one independent coordinate, whereas the Newton's second law you would have to write up for two coordinates. So we have to use now this expression, this Legendre transform, in order to get from our Lagrangian here to the Hamilton function. But before we can do that, we need to know what is actually the canonical momentum. Classical Hamilton function, which we have here, so it's the canonical momentum times the velocity minus Lagrangian. And the canonical momentum, or generalized momentum vector, canonical conjugate, it has several names, is defined in this way. You can obtain the component of the canonical conjugate to the position vector, canonical momentum, as this taking the derivative of Lagrangian with respect to the corresponding component of the velocity vector. Another exercise which you're going to do shows you that if you do that, then you find that the canonical momentum is the mass of the electron times the velocity minus the elementary charge times the vector potential. That means that the canonical momentum P, or the canonical conjugate momentum P, in the presence of electromagnetic fields, here represented by this vector potential, is no longer just equal to the product of mass and velocity. The product of mass and velocity, that's also momentum, but that's called the mechanical momentum or the kinematical momentum. And we use the simple P for that. So that is mass times velocity. And you can see it's not equal to the canonical momentum here, but it's a canonical momentum plus the elementary charge times the vector potential, or in general terms it would be minus the whatever charge of particle you have times the vector potential. This momentum P here, mass times velocity, that's called the mechanical or kinematical momentum, because that's the one which you need in order to calculate the kinetic energy. So the kinetic energy is defined here with P. So it's P squared divided by 2me. That's the kinetic energy. Whereas the canonical momentum here is the one which enters into the classical Hamilton function, and that's also the operator which we normally have in quantum mechanics. The one which we had in... Oh, what we have to do now, we have to insert this canonical momentum in our expression for the... We do that, which we can get from here just by isolating the velocity from this equation. And if we insert then this, then we get this expression here. So we get the classical Hamilton function as the mass times the velocity squared divided by 2. That's the kinetic energy, minus E times the scalar potential. However, in order to apply the substitution rules, in order to get to quantum mechanics, we need to write the classical Hamiltonian function in terms of the canonical momentum and not the velocity. So we have to, once again, insert the relation between the canonical momentum and velocity twice squared. Then we arrive at this final expression for the canonical momentum in the presence of electromagnetic fields. You can see here we have the canonical momentum plus the elementary charge, because we are talking about an electron, times the vector potential and squared. Now, applying now what we can, because now we have the Hamiltonian expressed, the variables are position vectors and canonical momentum. Now we can apply the substitution rules. So from the classical Hamiltonian function, we get to the Hamilton operator and the classical momentum, canonical momentum, or generalized momentum becomes the momentum operator, which please remember that is equal to minus I h bar and the gradient operator. Now you can see we have here a squared, and that's not always very convenient. So let's write out this square parenthesis, which of course in the first place gives us 4 terms, gives p squared plus e squared times the vector potential squared, and then it gives us the 2 cross terms. But as you will see in some of the exercises, by using what is called Coulomb Gauge, and the Coulomb Gauge is defined by the fact that one sets divergence of the vector potential equal to 0. That has no effect for, as you can see in some of the exercises, no effect for the magnetic field. So the vector potential is still able to reproduce or to represent the magnetic field exactly, but we can choose the divergence to be 0. If we do that, then we get 3 terms. We get here the normal kinetic energy term, as we know it from the field for Hamiltonian. We get the vector potential squared, and we get this term with the vector potential dot scalar product with the canonical momentum operator. And then we have an extra term, which is the scalar potential. So you can see the external electromagnetic fields via their potentials enter in basically in 3 places in the Hamiltonian. You have the electrostatic potential as an extra term, and that's basically, I mean, it's precisely like the Coulomb interaction of the electrons with the nuclear charges. That's also an electrostatic potential. But the vector potential, and therefore the effect of magnetic fields, you have twice. You have a linear term here in scalar product with the canonical momentum, and in addition you also have the square of the vector potential. And in the following chapter we will come back to the fact that here we have the vector potential showing up linearly and quadratically.